This is a help video for the DC Operational Amplifiers game in Circuit Tutor, Level 1, Problem Type 1. So we'll go ahead and go into that game. And I'm going to generate a random example here, or a random problem. Now, before we're doing this, of course, we should always read the introductory tutorial, which will be available on the website when that's completed. And then after doing that, it would be a good idea to look at some examples. So I'll just show a typical example here just for brevity. And so you see here we have a problem with an op-amp, which of course is a symbol. And we notice first of all that this op-amp does have proper negative feedback going from the output of the op-amp back through the resistor towards the negative input, which is the way we need to operate it to have stable behavior. And to analyze this, it's done very similar to what we do for normal DC nodal analysis, with one little quirk. We generally cannot do readily a mesh analysis on op-amp circuits, so we always approach it from a nodal analysis point of view, and that's because there's things hidden inside here in the op-amp equivalent circuit model that basically would make it difficult to do mesh analysis. You might even have a non-planar circuit. So this shows writing a voltage constraint equation, so just the normal thing we do for nodal analysis, which is covered in the DC nodal equations and DC nodal solutions tutorial. So that fixes V3 at 3 volts. And then there's a special equation now for operational amplifiers. When they have this negative feedback as shown here, they try to keep their two inputs have almost exactly the same voltage because of their very large gain. And ideally we assume that this voltage in fact is the same, even though there's no current going into the negative terminal and no current going in or out of the positive terminal either way. So in this case it might even be called a virtual ground or a virtual short between these two inputs. So that means that whatever the voltage is here has to be the same as this voltage. This is what we call an input voltage constraint equation, and that just means in this case that V1 has to be 0. Then we need to write KCL equations for each unconstrained non-reference node or supernode. And notice that we don't choose the reference node typically in an op-amp because that's also the ground for the amplifier itself, and therefore it's not really practical to change that ground in the circuit like the way we do with normal circuits that don't have op-amps. So that's always going to be pretty much a fixed thing and will be given to us. And that's one difference between op-amps and normal problems. So here we're going to write a KCL equation for node 1, which is the negative input. Clearly, and also I should mention that these multiple ground symbols are very important. What that means is there's an implicit connection between those 2 points where there are multiple grounds, which is something that we don't typically do in other types of circuits, but it is a very common convention in electronics to have those multiple ground symbols to avoid cluttering up the diagram with lots of connections between all the different grounds. So we cannot write a KCL equation for the output of an operational amplifier because, as you will have learned in the introductory tutorial, this is equivalent to a dependent voltage-controlled voltage source where the input voltage is the difference between the positive and the negative value on the input, the voltages, and that controls a voltage-controlled voltage source here connected to the output. So because this is connected in effect to a voltage source, even though that's not shown explicitly in the symbol, that means that for the usual reason we cannot write a KCL equation for this terminal. Because we don't know the current through a voltage source a priori, and therefore cannot solve the problem that way. But we don't need to do that either, because it turns out we'll still have enough equations for the unknowns. So what we do need to do is to write a KCL equation for the input of the op-amp. And so we're going to sum up all the currents leaving this node. Now, there's going to be a current through that resistor to node 3. There's going to be another current through this resistor to node 2, which is the output of the op-amp. And you might think, oh, well, there could be a current here as well. But remember that the negative input and the positive input, neither of those support any current in an ideal op-amp. Real op-amps have a very tiny current there, but we're going to neglect that for purposes of the ideal model. So therefore, we just have two currents to add up, which are illustrated here and color-coded. So the current through the 9 ohm resistor leaving node 1 will be the voltage of that node minus V2 divided by the 9 ohms. And then the current leaving node 1 to node 3 will be V1 minus V3 divided by that resistance. So this is just a standard KCL equation that should be very familiar, hopefully, from doing prior DC nodal analysis. Then this has been converted. These three equations have been converted into simplified nodal equations, which is straightforward here. The V1 terms have been combined. The 1/9 plus 1/2 have been combined to 0.6111 V1. V2 is minus 1/9, which is minus 0.1111. And then the minus V3, it's 1/2 V3, so that's a minus 1/2. And then the last equation, of course, well, I'm sorry, that was the last equation. The other equations are very simple because they just say, for example, V3 times 1 equals 3 and V1 times 1 equals 0. That's put into a matrix here, very straightforwardly. And then the slot variable equations, we're asked to find also the current through this voltage source in the upwards direction here. In other words, the current that's basically supplying to the circuit. And based on the fact that it's also the current through this resistor, we can just use the Ohm's law for this resistor to get that current. So we have V3 minus V1 divided by the 2 ohms. If it wasn't in series with the resistor, then we'd have to add up multiple currents here with KCL. But in this case, that's fairly trivial because there's only one. And then the slot variable also is the V2 with respect to ground, or V2 minus V0, the ground potential. And that's really considered a non-branch voltage in this circuit, neglecting what's going on inside here. And therefore, that's just equal to V2 because V0 is 0 by definition. And then those equations are solved, which really is fairly simple. We just would substitute these into here and then solve for the output voltage would be negative 13.5 volts. And in this case, that current would be 1.5 amperes. So that would be current flowing basically from the 3 volt to what's effectively a ground here. V1, remember, is effectively a ground because it's 0 through the 2 ohm resistor. So it's just, again, from this formula. Okay, and you can also see the Gaussian elimination steps, but honestly, if you're using Gaussian elimination to solve this problem, you're really not doing it a very good way. But it does have the ability to show it to you if you really are determined to look at it from that point of view. You can do it with Gaussian elimination as shown here, but it's much easier just to substitute. Okay, so let's go ahead and go into an actual problem here, which will be randomly generated for us. So this one looks a little bit different, and we'll have our usual instructions shown here. And you can also bring those up anytime you need them by clicking this help button. And there will also be a video help button, which in fact you've probably already clicked in order to view this, this help video. Okay, so we need to first write equations for this, as we discussed. So we're going to begin by doing a voltage constraint equation, since there is indeed a voltage source here supplying the voltage to the input of the op-amp circuit. And so that's quite straightforward. That just basically says that V1 will be equal to a certain fixed voltage, which is the output of that source. And so we type V1 there. It's really V1 minus 0, but we don't need to include the 0. And then that's going to be a negative 5 volts because it's connected to the negative side of a 5 voltage source. So we'll just put in negative 5 volts there, and we'll check that. That is correct. And that's the only voltage constraint equation. Then we have to do an input constraint equation. This is a new type of equation that we didn't do for other circuits because we didn't have op-amps. So this is always a pretty simple equation. It just says that the difference of V plus minus V minus is 0. Because, again, the negative feedback, which, again, notice here there is negative feedback from the output to the negative input, ensures that the voltage difference here is 0, or you can think of it as a virtual short. It's an unusual kind of short because it doesn't have any current, but yet it somehow manages by feedback to maintain 0 voltage there. And so here, that just means that V3 is going to be 0. And so we just put V3 there. And again, it's really saying that 0 minus V3 is 0, but that's the same as saying V3 is 0. So that's fine to enter that. Then we have to write a KCL equation. And for this type of what's called an inverting amplifier, that's always going to be at the input of the op amp. We can't do it for node 1 here because it's connected to a voltage source. And we can't do it for node 2 because that's connected to the output of an op amp, which again is effectively a dependent voltage-controlled voltage source. And therefore, that's not possible to write that because we wouldn't know the current basically coming out of the op amp. Okay, so we will go ahead and select KCL equations, and we will select node 3. That's the only one for which we can possibly write equation. And notice again, we're not selecting a ground here because that's already defined by the way that the power supplies are connected to the op amp. The power supplies exist here and are not explicitly shown. Okay, so now we're going to have a current going this way, so that'll be a difference in voltages, and a current going this way, again a difference in voltages, and only those two currents leave it. We don't include any current here because that current would be identically 0. Remember that the inputs of the op amp do not have any current, therefore we just set that all equal to 0. And now we can write those equations. So the current going through the 9 ohm will be simply V3 minus V2 divided by the 9 ohms, and then the current going back through the input resistor here will be V3 minus V1 divided by that 3 ohms. And those must add to 0, so we'll check that. And that is correct. And then finally, we need sought variable equations. So we want the power dissipated in the 9 ohm resistor, which is what we call the feedback resistor here, that connects from the output back to the negative input. So we can go ahead and select sought branch power here. It is across one element. And it reminds us that we have 3 terms, or sets of terms rather, in our palette, which we may need. And so, for example, if I change that, I get some additional terms. Here I get some additional terms. They just don't all fit onto one palette, so that's why we have those 3 terms. So here we want to find this power dissipated in the 9 ohm, and that will be equal to something. And if we think about it, basically we know these 2 voltages, and we can use the standard formula for that. We could just compute perhaps the value if we wanted to, but well, that would presume actually we know this value, which I haven't computed yet, so we won't do it that way. We'll just do it in terms of node voltages, which is one way. If you do know the numerical answer, you can always just put it in this way, and that would actually be the fastest way to solve the problem. Okay, so here the polarity doesn't matter because this is being squared, so we'll just take V2 minus V3, or it could have been V3 minus V2, and then that's all divided by 9 ohms because that's V squared over R is the formula for power dissipated in a resistor, as you hopefully remember. So now we'll just check that, and that is correct. And then finally, the value of V2 referenced to ground, which is our node 0, that's a non-branch voltage technically. So we have to scroll down here and find the sought non-branch voltage, and that would be V20. It's not a branch voltage because it does not appear across any one branch of the circuit. And the op amp is really not considered a branch because it's a 3-terminal element rather than a 2-terminal element. Only 2-terminal elements are considered branches in circuit analysis. Okay, so this is going to be basically just equal to V2 because V0 is always 0. So that's usually a very simple equation to write. And we can just check that. And that is correct. And now we've written all the necessary equations here. We can count that we have 1, 2, 3 unknowns, and therefore we have 1, 2, 3 equations, not counting the sought variable equations, which are extra. So we can write no more equations now. And now it tells us we need to simplify these equations. To be honest, it probably isn't necessary to do that in this case, but just to be consistent with our normal procedure, we'll go ahead and do that. And so here, the first one says V1 is minus 5, so we'll just give V1 a coefficient of 1. And then we'll go over to the constant and make that minus 5. And that very succinctly expresses that. The others not being involved, so those have 0 coefficients. The second one just says V3 equals 0. So we have to, of course, put a 1 in front of the V3 so that that's a meaningful equation. And then this will just be 0, the default. And then the third equation, the V1 has a coefficient of minus 1/3. And I am now, in the newer versions of Circuit Tutor, allowed to enter a fraction there, so I can go -1/3, and it'll actually convert that to a decimal for me automatically. So, or you could enter it as decimal if you prefer. Then the V2 coefficient, we have -1/9 in this equation, so that would be just minus, and again I can just type it as 1/9 if you want. You probably know that that's -0.1111. And then the V3 coefficient, now we have two terms, so we have 1/9 plus 1/3, or 1/9 plus 3/9 if you will, so that's going to be 4/9 altogether for V3. And 4/9, as you probably know again, well, we can just type it as 4/9, but it will change it to 0.4444. And then the constant here is going to be 0. So that constitutes our equations, very simply. We'll check that. And by the way, if you don't want to do all this, you could skip to the final answer entry and just put in the number if you want. That could save a lot of time, actually. And in this kind of problem, that might actually be a good idea if you already know the answer. Okay, and now it's asking us to convert to a matrix equation, even though, to be honest, we would never probably want to solve it that way in this particular problem because it's so simple, but we can copy those and it won't take any time. And once again, if you wanted to enter that as 4/9, I could do that, but it's easier just to copy it. So we'll check that, and that is correct. And now it tells us to solve the matrix equation. Well, like I said, we'll really want to use substitution to do that, and I don't think we're really going to even need to work anything out on paper here because we can just simply say, well, let's look at this equation, which is the KCL equation. So all we have to do is say V3 is 0. Well, that gets rid of this term and this term. And that makes a very simple equation. It basically says that the V2 is going to be equal to -9 ohms divided by 3 ohms times the input voltage, which is just going to be V3, or -5. And so we know right away V1 is -5. We'll just put that here. And we know also that V3 is 0, so that's already entered. And then again, this is going to be 9 divided by 3, which is a gain of 3. And it's actually -3 because it's an inverting amplifier, which you get from this formula also, times the input voltage, which is -5. So -3 times -5 is going to be positive 15 volts. And if you know about inverting amplifiers, you might actually have known that right away because the input voltage here is a -5 volts. And you may actually just remember from the universal case that's discussed in the introductory tutorial that the gain of an inverting amplifier here is minus the feedback resistor divided by the input resistor. So it's -3. And so we could have just gotten that really at the very beginning without going through all of this rigmarole here. And perhaps as you gain experience, you'll just put in that answer at the very beginning, which you actually have the option to do when you're entering a sought variable. I could just put in a number, and if I do that, I don't need to do any of the rest of this, including writing these equations. It's not really necessary. It's probably good to do it a few times just so you understand the principle, but once you've done it a few times, you'll know the answer. Okay, so we'll check those answers, and that is correct. And again, the last thing you'd probably want to do would be do Gaussian elimination, unless you really want to do a lot of extra work. But if you'd like to do that, I guess you can. Okay, and then we're just going to calculate those sought variables based on the numbers we just computed. So the dissipated power, again, that's V3 minus V2. So that's just going to be 15, basically, since we don't care about the polarity. 15 squared divided by 9. So that would be 225 divided by 9. So I'll put that in, just, oops, sorry about that, on the calculator. And something else there on my clipboard, I guess. Anyway, I'll just do that very quickly. So that's 225 divided by 9, and that's 25. And then V2 naught is just V2, which we already have, is 15. So I'll just put 15 there. And again, you could have entered these back at the beginning if you want to, but we'll check those, and those are correct. And that will generate a PDF transcript of your work, which is being shown here. And basically that'll show all your correct and incorrect steps. The incorrect ones will be in red if you made any mistakes. but basically it'll show you the complete solution to the problem. And we can always access that from the review work module. And if I want to see a detailed explanation of this, I can click yes here, and it'll basically just sort of walk me through that one KCL equation and give a little bit more detailed explanation than you would otherwise have here. And you can of course get detailed explanations of the op-amp input constraint equations, the voltage constraint equations, and the KCL equations if you need that. And you can also look at the Gaussian elimination again if you wanted to do that. So we'll just close that out. And again, if you need your transcript, that's available from the review work button. So that completes this problem.